This video is going to go over a chapter 6 problem, number 9. And this problem is entitled Applying the Michaelis Menten Equation. You're told that you are given some information about a enzymatic reaction where an enzyme called hapiase catalyzes this reaction, and they're doing these researchers are doing an experiment to characterize the enzyme. And so in the first part, in part A, you're told that the total enzyme concentration that's being used is 4 nanomolar, and they find that the Vmax is 1.6 micromole per second when they use that much enzyme. And based on this experiment, what's the kcat? And we know that kcat is the rate of the slowest step. So it's the rate limiting step of the entire thing. And if we wanted to calculate the kcat, and we're given total enzyme and Vmax, we can do it pretty straightforward. The fastest you can go is limited by the slowest step of the enzymatic process times the total amount of enzyme that you have. And so then we can plug in our total enzyme here, 4 nanomolar. We're solving for kcat. Our Vmax, because we're plugging it into the same formula, we have to make sure that it matches the other units. So 1.6 micromole per second. There's a lot of ways to do conversions. Everyone does it differently. Micromole is 10 to the negative 6. Nanomole is 10 to the negative 9. So I know I have to move that decimal point 3 places to the right. So the new number is going to be 1. So I moved it 1, 2, 3 places to the right, and that's nanomole per second. Now I kind of just did that in my head a little bit. I didn't do any official algebra. But by all means, do the cross multiplication or do the conversion table if you do that. Whatever method you do for your conversions is fine. And you just want to make sure that your units match when you're plugging numbers into the same equation. So from here, you just divide both sides by 4 nanomolar so that you get a kcat, which equals 1600 nanomolar per second over 4 nanomolar. And that equals 400 per second, which is your kcat. So let's look at part B of this problem. We've got, let's see, you're told you're in another experiment and you have a total enzyme concentration, in this case, of 1 nanomolar. And your substrate concentration, which is happy, your substrate, is 30 micromolar. And you find that using this substrate concentration, your initial velocity is 300 nanomolar per second. And asking you what is the Km of hapiase for its substrate happy. So you can calculate your new Vmax. So that's Vmax equals kcat times total enzyme concentration. Your kcat is a characteristic of the enzyme. So you use that number, you've already derived that number in the previous part of the problem, and the kcat was 400 per second. And in this case, your total enzyme concentration is 1 nanomolar. So your Vmax is going to be 400 nanomolar per second. So the solutions manual for the textbook moves some stuff around to make the algebra much easier, but I'm just going to go with the plug it into the original Michaelis Menten equation and do some algebraic steps to sort it out. I think that's a little bit easier to follow. So your Michaelis Menten equation is initial velocity equals Vmax times substrate concentration over Km plus substrate concentration. So from here, I'm going to be plugging in this number, this number, this number, and this number, because we know all those, and we're solving for Km. So it's pretty straightforwardly plug and chug. The only thing that you have to be careful, though, is to make sure that all your units match. So right now they don't. We have our substrate concentration in micromolar, but our velocities are in nanomolar. So I'm going to convert my velocities. 300 nanomolar per second is 0.3 micromole per second. 400 nanomole per second is 0.4 micromole per second. I just did that quick and dirty pretty fast, moving the decimal point 3 places to the left, but again, write your conversions out if you need to make sure that you don't make any mistakes. So from this point, we can plug in our initial velocities 0.3 micromole. Let me erase that so it doesn't look ugly. So 0.3 micromole per second, our initial velocity. Our Vmax is 0.4 micromole per second. Our substrate concentration is 30 micromolar. Our Km is what we're solving for, and our substrate concentration is 30 micromolar. To make this easier to follow, I'm going to rewrite this at the top of the page so that we can do all the algebra. So starting from the top, we had 0.3 micromole per second equals 0.4 micromole per second times 30 micromolar over Km plus 30 micromolar. I'm going to cross multiply here, and this is 0.3 micromole per second times Km plus 9 micromolar squared per second equals 0.4 times 30 is 12 micromolar squared per second. So we've got 0.3 micromole per second Km. I'm going to subtract 9 from both sides of the equal sign. So I'm left with 3 micromolar squared per second. And then I divide both sides by 0.3. And it's going to be 10. And it's going to be 10 micromolar because the other units cancel out. And that is our answer. I'm going to check with the solutions manual. And that's what they got too. Their method was just a little bit different, but this works just as fine as well.